Hey everyone, and welcome. Today, we're totally mastering Chapter 10 of your science textbook. We're going to be decoding everything from the literal living, breathing camera inside your head all the way to the grand optical illusions painting our sky. This explainer is designed to build your conceptual mastery from the ground up, so get ready to see the world in a completely different light, literally.
So here is our roadmap for today. We'll start with the human eye camera, look at fixing vision defects, check out prisms and dispersion, dive into atmospheric refraction, explain why the sky is blue, and wrap up by checking your understanding. Let's just jump right in.
Section 1. The Human Eye Camera.
Okay, let's dive into the incredible organic camera sitting right inside your skull. Imagine light entering your eye. First, it hits the cornea. That's the transparent bulge on the very front. Right behind that is the iris. It's a dark, muscular diaphragm that controls the pupil, and it acts exactly like a camera's aperture to regulate how much light gets in. Finally, your crystalline lens focuses this light to form a real, inverted image on your retina. And from there, the retina sends electrical signals through the optic nerve straight to your brain, which brilliantly flips the image right side up so the world makes sense.
But you know, your eye is actually far superior to a basic camera, all thanks to a literal superpower called the power of accommodation. See, your eye lens isn't made of hard glass. It's this flexible, jelly-like material. When you look at distant mountains, your ciliary muscles relax, the lens gets thin, and the focal length increases. But what about when you're reading a textbook close to your face? Those same muscles contract, which makes the lens thicker. This allows you to focus flawlessly all the way down to what we call your near point, which is exactly 25 centimeters. Try reading anything closer than that, and you'll definitely feel the strain.
Moving on to Section 2, Fixing Vision Defects.
So, what happens when this perfect biological system falters a bit? Let's step up to the whiteboard. First up is myopia, which you probably know as nearsightedness. This is when you can see nearby objects perfectly fine, but distant mountains look super blurry. Why does this happen? Well, the eyeball has become too elongated, or maybe the lens has excessive curvature. Because of this, the image of a distant object focuses in front of the retina instead of on it. To fix this, we just drop in a concave lens. This diverging lens spreads the light rays out just enough before they enter the eye, pushing that image neatly back onto the retina where it belongs.
On the flip side of that, we have hypermetropia, or farsightedness. Here, distant objects look great, but reading a book is a huge struggle because your near point has actually receded past that 25-centimeter mark. In this case, the eyeball is too small, so light rays from close objects try to focus behind the retina. The fix for this one? A convex lens. This converging lens gives you the extra focusing power you need to bring those rays together sooner, forming a nice sharp image right where it needs to be.
Let's lock this in your memory right now, guys, because this is an absolutely fundamental concept. Myopia pulls the image forward in the eye, so it needs a concave lens to push it back. Hypermetropia pushes the image back behind the retina, so it needs a convex lens to pull it forward. It is all about adjusting that focal point.
Now, as people age, another defect called presbyopia often kicks in. The ciliary muscles just naturally weaken over time, making it really hard to see nearby objects. And actually, some people end up suffering from both myopia and hypermetropia at the exact same time. For that, they need bifocal lenses. That's a concave lens on the top half for distance and a convex lens on the bottom for reading. Separately, older individuals might also develop a cataract. This is a condition where the crystalline lens itself gets milky and cloudy, causing vision loss. But the good news? It can be entirely corrected with a very routine cataract surgery.
All right, Section 3, the Prism and Dispersion.
Let's step out of the biology lab for a second and jump into physics to play with some glass prisms. When we track a ray of light passing through a triangular glass prism, we get to witness the magic of refraction. The light enters the glass and it bends towards the normal. Then, as it exits back out into the air, it bends away from the normal. Because of the prism's really unique, angled shape, the emergent ray is bent at an angle compared to the original incident ray. We call this specific, measurable bend the angle of deviation.
But you know, the prism does something even more spectacular than just bending light. It causes dispersion. If you pass a beam of white sunlight through it, it splits into this spectacular, gorgeous band of 7 colors. Just remember the handy acronym, VIBGYOR. So, why does this happen? It's because different colors of light actually bend at different angles. Red light bends the least, and violet bends the most. Fun fact, Sir Isaac Newton actually proved this by using a second inverted prism to recombine all these spread out colors right back into white light.
And the coolest part is that nature scales this whole process up perfectly. Every single time you see a beautiful rainbow after a rain shower, there are millions of tiny water droplets suspended in the atmosphere acting as tiny, natural prisms. Sunlight enters the droplet, refracts and disperses into its component colors, reflects internally off the back wall of the droplet, and then finally refracts again as it exits. This magnificent, complex interplay of dispersion and internal reflection is exactly what brings that colorful spectrum straight to your eyes.
Next up, Section 4, Atmospheric Refraction Magic.
Let's take these optical concepts to an even grander canvas, our very own Earth's atmosphere. Have you ever looked up and wondered why stars twinkle? Well, it is entirely due to atmospheric refraction. Our atmosphere is made up of layers of varying temperature and varying refractive index. When starlight enters, it undergoes continuous refraction, constantly bending towards the normal. This actually makes the star appear slightly higher in the sky than its actual position. But because our atmosphere is super dynamic and always moving, the path of those light rays constantly wavers, causing the starlight entering your eye to flicker. And there you have it. That is the magic of twinkling.
Okay, so if stars twinkle, here's a brilliant textbook question we really need to master. Why don't planets twinkle? The answer comes down to distance. Stars are incredibly, mind-bogglingly far away, so they act like point-sized sources of light. Planets, however, are much, much closer to Earth. We can think of a planet as an extended source, which is essentially just a collection of a huge number of point-sized light sources. While the light from individual points on the planet might waver slightly, the total variation in the amount of light entering our eye from all these points averages out to zero, so the flickering completely cancels itself out, nullifying the twinkling effect entirely.
And this brilliant atmospheric bending does something even more incredible for our daily schedules. It actually lifts the image of the sun right over the horizon. Because of atmospheric refraction, the sun becomes visible to us about 2 whole minutes before the actual sunrise, meaning before it has physically crossed the horizon line. Similarly, it stays visible for about 2 minutes after the actual sunset. So if you do the math, atmospheric refraction essentially grants us roughly 4 extra minutes of precious daylight every single day.
Let's move on to Section 5. Why is the sky blue?
We've talked a lot about refraction, but what actually paints our sky that beautiful color? This is all due to a phenomenon called the scattering of light. See, our atmosphere is packed with molecules and extremely fine particles that are actually smaller than the wavelength of visible light. When sunlight strikes them, they don't just scatter all the colors equally, not at all. They are highly effective at grabbing light of shorter wavelengths, like blue, but they let the longer wavelengths, like red, pass basically straight through. So, those fine atmospheric particles grab that shorter blue light and scatter it violently in every possible direction, creating our breathtaking blue canopy.
Understanding this scattering effect also answers a very practical safety question from your syllabus. Why are danger signal lights always red? Well, think about it. If blue light is scattered so easily by fine particles, what happens to red light? Red light has a wavelength that is about 1.8 times greater than blue light. Because of this much longer wavelength, red light is the least scattered by obstacles like fog, dust, or smoke. It cuts right through all that atmospheric interference in a perfectly straight line, meaning it can be seen clearly in its true bright red color from very, very far away.
Finally, Section 6. Check your understanding.
Fantastic work today, students. You have genuinely built complete conceptual mastery of this entire chapter. But before we go, let's lock it all in with a quick textbook exercise. Question 1. How does the eye focus on both that textbook in your hands and the clouds way outside your window by adjusting its focal length? What is the specific term that defines this? Is it A, presbyopia, B, accommodation, C, nearsightedness, or D, farsightedness?
If you guessed B, you are spot on. The answer is accommodation. Just like we discussed earlier, your hard-working ciliary muscles are constantly, tirelessly working to tweak that lens thickness and adjust your focal length so you can see perfectly across absolutely all distances.
I'm going to leave you with one final, really provocative thought straight from your textbook exercises. We now know the sky is blue here on Earth because of atmospheric scattering. But what does an astronaut see when they look out the window of the International Space Station? Without an atmosphere around them to scatter the sunlight, the sky doesn't look blue to them at all. To an astronaut, it appears as a perfectly dark, pitch-black void. The interplay of light and our environment is truly wonderful when you really think about it. Keep exploring, stay intensely curious, and I know you will absolutely ace this subject.